So gas laws can also be used in stoichiometry problems because you can solve for moles in the ideal gas law. So in a general sense, stoichiometry is grams to moles, right? To moles to grams, but you can also use PV equals nRT here. So you could solve for moles, or you could use volume, temperature, pressure to get to moles that way, and then solve a stoichiometry problem and figure out grams of products, for example. But there's a special kind of stoichiometry problem that I want you to be familiar with, and that's this one. And I do want you to be able to do this, and I'll do an example of it down here. They're rather lengthy problems. But this is a really fast one. It turns out at standard temperature and pressure, that number that we calculated before, 22.41 liters equals to 1 mole, can be used in stoichiometry problems for gas. So let me show you how this is done. You have how many grams of magnesium oxide are formed when 12.8 liters of oxygen gas measured at STP reacts with an excess of magnesium metal. So this is my equation, right? Hang on. Yeah, that's weird. It's supposed to be a 1 here, like that. There we go. So it's 2 magnesiums react with 1 mole of oxygen to produce 2 moles of magnesium oxide. So I'm going to write this. I want grams, right, of magnesium oxide, grams of MgO. I'm given 12.8 liters of oxygen at STP. And at STP, I know for any gas, it doesn't matter which one, it's 22.4 liters is 1 mole of oxygen gas. So that's O2, one of the diatomics, right? And then I know 2 moles of magnesium oxide for every 1 mole of oxygen. And then I want grams, and so what I need to have here is the molar mass of magnesium oxide. That will be, hang on, that's 40.30 grams for every 1 mole of MgO. And I just added the mass of magnesium oxygen together to get that. And so I can do this calculation. I can say, my calculator, here we go, 12.8 divided by 22.41, or 22.4. The book will use 22.4. You should probably stick with that, actually. I'll stick with that, 22.4, times 2 times 40.3. And that comes out to 46.057 grams of MgO. The units will cancel like this. Right, so that leaves me the grams of MgO. So that comes 46.1 grams, because it has 3 significant figures in it like that. Okay, so again, this what's called molar volume of a gas is very useful for doing stoichiometry problems as long as they're at STP conditions. So this last problem's an example of a stoichiometry problem using the ideal gas law. It's not at STP conditions. Okay, so this previous one we were at STP, and we could say 22.41 liters is equal to a mole. You can't do that if it's not at STP. So here it says you have 325 milliliters of hydrogen gas, and it's collected over water at 25 degrees Celsius, 748 millimeters of mercury. How many moles of zinc reacted? And it gives you the vapor pressure, or the partial pressure of water at that temperature. Or we could have gone to that table. It's the same value in the table. Okay, so we have a reaction between zinc, and it was supposed to be hydrochloric acid, but it turns out, I don't think I wrote that in here. So we have an excess of hydrochloric acid. Okay. This is actually a single replacement reaction. So the balanced the reaction will look like this: zinc solid plus 2HCl make zinc chloride. which turns out to be aqueous in this situation. HCl is also aqueous, plus H2 gas. Okay, so we have a reaction. We know there's 1 mole of zinc is equal to 1 mole of H2 gas. That's the stoichiometry that we have. And we know that we collected 325 milliliters of hydrogen gas at 25 degrees and 748 millimeters of mercury. When you see those three things together, you should automatically, like in this section especially, you should automatically think it's an ideal gas law problem. But then it has this number, right? And so you have to also think it's a partial pressure problem. So I'm going to write PV, right? Sorry, P, V, N, and T. And again, I'm thinking about R being 0.0820, or sorry, 21 is what we're using. Liters times atmospheres. Oops, sorry. Per mole times Kelvin, like that. And so I have to think about what my units are here, right? So my temperature, we'll start from the bottom here, that's 25 degrees Celsius. That's kind of like this nice one to start with, because you know you just had 273, so that's 298 Kelvin, like that. N is what you're solving for. My volume is 325 milliliters, so that's 0.325 liters. But my pressure, now I have a couple of different pressures, right? I have 748 millimeters of mercury. That's where the pressure was collected at. That's my P total, right? So I know that the total pressure is the pressure of water plus the pressure of hydrogen, hydrogen. So if I want just the pressure of hydrogen, that's what this has to be down here. I need to say P total minus the pressure of the water. And basically it always turns out you subtract the water vapor from the total pressure to get the pressure that you're looking for. So in this case I have 748 millimeters of mercury minus 23.8 millimeters of mercury. And that's going to be, 24.2 millimeters of mercury. Now I have a problem, right? Because this is in millimeters of mercury, but this is atmospheres. So you always got to be thinking about what's the units with R. So I know my pressure of hydrogen, I'm going to do 724.2 millimeters of mercury, and I'm going to convert that over 760 millimeters of mercury in 1 atmosphere, like that. So I'll calculate that value. So 724.2 divided by 760, that'll come out to 0.9529 atmospheres. And I can solve my ideal gas equation and plug my numbers in. So I know from previous problems, I know N is going to be equal to P times V over R times T, and I'll plug those numbers in. So pressure is 0.9529 atmospheres. V is going to be 0.325 liters. Again, that's a conversion. I do those in my head, and you should probably be close to the point where you can start thinking about things like that. But if you can't do that, then go ahead and just set it up this normal way and convert it. R is 0.0821 liters times atmospheres over moles times Kelvin times 298 Kelvin, like that. All right, so I plug that into my calculator. So 0.9529, only 3 sig figs in that, by the way, times 0.325 divided by 0.0821 and divided by 298 Kelvin, that comes out to be 0.01266. That's moles of hydrogen. All right, now that is almost completely done. I know if I want moles of zinc, right? So I'm looking for moles of zinc. And I have 0.01266, 3 sig figs, moles of hydrogen. And I know that there's 1 mole of zinc for every 1 mole of hydrogen. And you get the same number, but we switch the units now. We're in moles of zinc. So this is 0.0125 moles of zinc reacted like that. And you'll be doing, it turns out you'll be doing a problem very similar to this one in one of the other labs that we're doing probably this week.